quickly?
Yeah, so one is...
But it won't update.
Maybe.
What are the announcements? Okay, the best. Good, okay. Welcome to the class. We are discussing embeddings as we started talking about this topic last week. On Tuesday, I think. So what we will do today is talk more about embeddings, and in particular, we will talk about how do you generalize neural networks to graphs. And then next week on Tuesday, Michele will do a hands-on session. So we will make things that I'm talking about today more concrete. We will see how we can implement them in the popular deep learning frameworks, and how do we make everything I kind of talked today about at high level, how do we make it work, and how do we make it work in practice for various kinds of interesting applications. So here is what we would like to do. Right, we would like to learn this type of a function that will take our network and that will map or embed this network in some low-dimensional embedding space. And the idea is, right, that we want to do this kind of representation learning, where rather than trying to come up with a feature representation for the nodes, like, for example, we were using with graphlets, or the way we were doing with motifs for entire networks and so on, we would like this neural network to learn the structure, capture the structure of the network, and capture kind of the dependencies between the nodes. So our idea will be that we want to map these nodes into a d-dimensional space, into our representation space, using embeddings in such a way that nodes that are similar in the network get mapped close together. And the goal will be that we learn this mapping function, so that this mapping function is not just given to us, but we actually want to use some procedure to learn this mapping function. Right? And one way we can think about this is to say, I have my network, my complicated network here. I want to learn these encoding functions that will basically take the nodes in the network and map them into this low-dimensional space. And the position of the node in this space should somehow capture the structure, the position of the node in the network. So that's kind of what we are trying to do. And the idea is, right, as we talked on Tuesday, is that somehow the similarity, whatever that really means, in the network will be mapped into the similarity of these two objects in the embedding space. Here, that is just a dot product, so it's a cosine similarity, so nothing too fancy, right? But the fancy part is this mapping function. And what do we need to define to be able to make this work? We need to define this notion of similarity of the nodes, and then we need to define how this function, this encoder function, takes the node and how does it map the node. And we said that there are two key components to make this work. One is the encoder function that will take the node and learn how to map it. And then there will be this similarity function that will tell us the relationship between the input network and how to map that relationship into the embedding space. And to make this more kind of more concrete, the encoder function will take the node and give us the embedding or coordinates of the nodes, the feature representation of the node, and then the similarity that we define in the network will be, we'll try to make it such that the similarity in the network equals to the similarity in the embedding space. And you know, similarity here could be Euclidean distance. This is now a dot product, so this is just a cosine distance. It's the angle between the two vectors. That's the way you can, or cosine of the angle between the two vectors. And what did we talk about on Tuesday? We talked about these shallow encoding methods, as we call them, where the idea is that what we will do is we will try to learn this embedding matrix Z, where basically the number of rows is the number of dimensions, number of columns is the number of nodes, and for every node we just learn the coordinates, right? So we'll just try to directly estimate the coordinates of the nodes, right? And this is what we will do. So how would you think of this? The way to think of this is to say, I want to have this one-layer data transformation where for every node I learn a set of coordinates. Let's say here are the coordinates for the node. So I'm saying that the coordinates of the nodes should be such that when I dot product them here, the similarity of the coordinates equals to the similarity in the network, right? And now I can say, how do I best set these guys here so that their dot product equals to the similarity in the network? And then, of course, the question is, how do you define the notion of similarity? And we explored using random walks to define that notion of similarity. Now, what are some limitations of these types of approaches? So the first limitation that is very important is the number of parameters we are trying to estimate equals the number of nodes, right? Because for every node we try to estimate a set of coordinates. So if I know I'm mapping into, let's say, 100-dimensional space, and I have a network on 1,000,000 nodes, this means I need 100 million parameters. And if I have a network on 2,000,000 nodes, then I need 200 million parameters, because for every node I need to estimate 100 numbers. So this is why this makes it hard. Another thing that makes it hard is that these methods are inherently what is called transductive. So it means that if I learn how to embed one network and then another network comes by, I have to re-embed everything. And another thing that is important, if a network evolves over time, again, when a new node arrives, I need to estimate all of its coordinates, so I have to do all the work from scratch. So there is kind of no ways for the embeddings to generalize to new graphs or to new nodes I haven't seen during training. And then the last thing that is very important is that these methods directly learn coordinates of the nodes, and they do not incorporate node features. So the question is, if you have any attributes features on the nodes, how would you do that? Another thing I think that is important to realize, and I kind of didn't say that before, is that if you think about when we talked about spectral clustering, right, and we talked about finding the eigenvectors of the graph Laplacian, that's also an embedding method. Right? But if you think about those embeddings are computed by trying to optimize a very particular objective function, which was this objective function of trying to find clusters and so on. Right? So we already kind of talked about embeddings when we talked about spectral clustering. Only there the embeddings were very specific to identifying clusters. And here we want to learn these embeddings that are specific to the task we want to solve later, right? So if the task is clustering, the embedding should obey the clustering structure. If the task is link prediction, the embedding should obey link prediction, right? So today what we are going to talk about is to talk about what we call deep graph encoders, right? Where the idea will be that we want to take neural networks, generalize them to graphs, and be able to say, how do I encode a node? I encode the node through multiple layers of nonlinear transformations of the graph structure. Whatever this means, right? We'll make it precise, right? And the important point is that these deep encoders that we will be using can be combined with kind of any graph similarity function, even those defined in the last lecture. So basically what we'll talk about today generalizes what we talked last time. Pictorially, what we would like to do, we'd like to take our graph, send it through some deep neural network, And out here, good predictions will come. So basically, we will get good node embeddings that can be then used to make various kinds of predictions about the nodes. We would like not only to embed nodes, but we'd like to embed entire graphs, subgraphs, things like that, right? So there is a lot we would like to get out here through this kind of picture. However, this is amazingly challenging to do. And the reason why this is challenging to do is that basically present machine learning, deep learning toolbox we have is specialized to simple data types. Essentially, all we know what to process is fixed size grid graphs, right? If you think of the images, all the images have the same structure, have the same size, so you can just think of them as fixed size grid graphs, right? And if you think about text and speech, what kind of graphs are these things? They are sequences, so they are line graphs. Right? So essentially, from what we care about in this class, these are extremely boring graphs, right? Extremely boring simple data, a fixed size grid or a line graph, right? Here you can have a notion of a sliding window, and here all the graphs are the same, so you know how to pipe them through the network. So the claim is, right, that modern deep learning toolbox is designed for this kind of simple data types, sequences and fixed size grids, right? But if you think about graphs, graphs are not fixed size grids, right? They have arbitrary size, they can have variable number of nodes, they have much more complex topological structure, and what is also important is that images have this nice two-dimensional structure, and it's clear what is top left and it's clear what is bottom right. Text has or speech have this very linear structure, so it's clear how to go left and how to go right? It has structure. If you think about networks, networks have no reference point. It's not clear what's top left, what's top right? So there is no singular reference point. So it is very, very hard and unclear how to do deep learning on top of these types of data, right? It's fundamentally different. We don't know how to resize graphs, things like that. Okay, so what we would like to do, at least conceptually at the intuition level, philosophical level, is if you think about what made kind of advances in computer vision is this notion of a convolutional operator, where you basically have this convolutional operator window that you are sliding across your image. And it's very nice, right? You have the two-dimensional image and you are just sliding that operator kind of line by line or however you decide to slide it and compute some function over that sliding window, right? You can do this and pass it through many layers and you get good results. So the goal is to generalize this beyond this type of simple two-dimensional lattices. And if we are able to do this, then we'll be able to kind of leverage node features and attributes, right? In a sense that if in convolutions you have three channels, red, green, and blue, here you can also think of features as different channels. But of course, our graphs are not these two-dimensional, fixed size, well-oriented positioned lattices, but they are much more complex. But here is an insight that will allow us to generalize the notion of convolution to these complex data types. The way you can think of a convolution is that it basically takes a little sub-patch of the image, a little rectangular part of the image, applies some function to it, and produces a new part of the image, produces a new pixel. So the way you could think of this, in some sense, is that if I take this 3x3 patch here, I can think of it as a 3x3 patch. These are different pixels. And what happens is that essentially the center node of the center pixel aggregates information from its neighbors as well as from itself to produce a new value, right? So the idea is that the way you can think of this is you can think of this about convolutional operator as a way to transform and aggregate information, right? You collect messages from your neighboring pixels, combine it with your own message, and you produce your new value, right? So that's how you can think of this. So now the question is, if you have graphs that are more complex, how would you define the notion of this sliding window over these types of graphs? What would we do, right, for the networks that we care about? So here is one kind of poor man's attempt how to do this, and it will be quickly clear that this doesn't work, right? So imagine I have a graph on 5 nodes. I can represent graph on 5 nodes as an adjacency matrix, right? So here's the adjacency matrix of this graph here, and then imagine that each node has some attributes, some features. Let's say these are the features the nodes have. So what I could do is to say, oh, this is now a nice fixed size input, so let me just take this row and add it as an input to my deep neural network, right? And you would say, great, let's go and learn this. There are many reasons why this is a terrible idea. The first reason why this is a terrible idea is that for a graph on n nodes, you will have n rows of data. So you have n data points to train on. But if you think how many parameters this thing has, it has many more parameters than you have data points to train on, right? Because it has the number of inputs is the number of nodes plus the number of features. So even in the first layer, you have already used more parameters than you have training data points. As you make the network deeper, it gets even worse. So that's one important thing. Another important thing that this won't work for a graph on 6 nodes. Right? If you give me now a graph on 6 nodes, I don't know what to do, right? Then this matrix would be 6 by 6, but then I don't know where to add that additional node. So I don't know what to do. And then there is another issue, is that right now we labeled the nodes as A, B, C, D, E. But I could label them as A, B, C, D, E. And then the ordering, this adjacency matrix would change, would shuffle. And then the inputs to this matrix, to this network would also change. And it would get completely confused, right? So the point is that graphs are invariant to node ordering, right? You should get the same result regardless of how you order or how you number the nodes, right? So these are the 3 reasons why this won't work. Yes?
Can we order the node by the node properties like degrees, cluster efficiency?
You could, great, good. You could come up with some heuristic, and one heuristic would be to say, let me order the nodes somehow. But the question is always, what do you mean? Like, you could order them by degree, but then some nodes will have the same degree. So what do you do? Right? You could keep adding other properties. Perhaps that would work, but still, you won't be able to learn anything because you have too many parameters. Right? And then, yeah, I don't know. Let's just say this is a terrible idea. But if you are excited about it, you can do a project and prove me wrong or something, right? But it should be kind of clear why you don't want to do this. So let me tell you what you wanna do, right? This is what I want to talk to you about. I want to talk about kind of core deep learning for graphs today. I want to talk about graph convolutional neural networks. I want to talk about how to add attention, so graph attention networks, and I'll define what do I mean by this, and then give you some ideas and demos and things like that. Okay? So let's talk about kind of the core, how do you think of deep learning for graphs? All right? And the key concept here will be about understanding local network neighborhoods, and we will talk about different data aggregation strategies and define this notion of computation graphs. And then as we talk about this kind of at the single layer level, we will talk about how do we go deeper, how do we define the models, parameters, how do we train, and then how do we do unsupervised as well as supervised or semi-supervised way of training these things. So here is the setup for the rest of the lecture today. We will assume we have a graph that has some vertex set, has the adjacency matrix, vertices have some set of features. Features could be, if we are in a social network, it could be a user profile, or the feature vector could be simply the image the user has. In biological networks, this could be gene expression profiles, or if we have no features, things can still work. We could, for example, use indicator vectors, one-hot encodings as they are called, of the nodes. We could even use a vector of all constants as a feature vector, things like that. So this is what people use when they don't have any features. And the key kind of insight today will be that the underlying network, the social network, we can think of it to define the computation graph. So it means that the social network defines the neural network. That's the key, right? So the idea is that the node's network neighborhood will define the computation graph. So the way we will think of this is that given a node and we want to make some prediction for the node, we will first figure out what the computation graph should be. And then we will use this computation graph to propagate and aggregate information from the neighbors and neighbors of neighbors to make a prediction at node I. right? So this means that what we will learn is we learn how to propagate information across the graph to compute a representation for the node. And why this will be amazingly powerful is because this propagation will capture both the structure of the network around node I, as well as we learn how to borrow information from the nearby nodes to enrich the description or representation of node I. Right? So we are doing two things at the same time. We are capturing the structure and we are also borrowing feature information. Right? And this means this will be strictly better than trying to classify node I by itself using its own features only, because we'll be able to borrow the signal from the nearby nodes. Okay? So here is the key idea. The key idea is that to create a network embedding, we want to use the local network neighborhood to define the neural network structure. Right? So if I have this tiny graph here as an example, and I want to create an embedding for node A, then the way I can do this is to say, aha, node A has to aggregate information from B, C, and D. So node A gets information from nodes B, C, and D. And for example, node D here has only one neighbor, A itself. So this guy collects information from A. While, for example, node C here gets information from its neighbors, which is A, B, E, and F. So there is A, B, E, and F. Right? So you see now how I basically took the node in the network. The node in the network collects information from its neighbors. That's the one layer. And then I unrolled this one more layer to say, aha, and now each of these nodes collects information from its own neighbors to be able to compute the representation. Right? So the point is that now we have a two-layer neural network that makes some prediction for node A. And you can see how now the prediction that we make at node A will depend on the feature representations of all these other nodes. Right? So in some sense, we will learn how to combine information from the neighbors and neighbors of neighbors to make a more accurate prediction for node A. This is what we will do. Yes?
When should we know when to stop the unrolling?
Great. When do we know when to stop unrolling? In practice, people don't go too far. People would go 3-4 steps. Why would you only go that deep? You can think for yourself, but I already gave you the answer earlier in the class. The reason, would anyone guess why you don't want to go deeper than 4 or 5?
More parameters.
What's the diameter of networks? What is the diameter of the MSN network? Do you guys remember that? 6. Equals 6. Right? So it means if I go 6 levels deep, I visited every node in the graph. So I don't need to go 6 levels deep. Right? So the depth here is very different than the depth in computer vision. Right? Here you go deeper in the network, and if you go 3-4 hops away, you essentially visited a huge chunk of the network, and you don't need to visit the huge chunk of the network. So the depth here is a different concept than the depth we like to think about. Okay? So this is the intuition part. And of course, what will these boxes be? These boxes will be some kind of neural networks that will aggregate information. And what is important? There is one important property these boxes need to have. This aggregation needs to be order invariant. Why do we care about order invariance? Because if I renumber the nodes in some different way, I reorder the way I aggregate these guys, I permute them, I should still get the same result. So these aggregations have to be order invariant. Right? So an average is an order invariant function, or a maximum is order invariant function. But something that takes the second element is not an order invariant function. So these aggregation functions, as I will show you later, the important property is that they are order invariant. Yes?
Do you share parameters across the different neural networks?
I will come to that. So let me not answer yet. But I will answer your question, definitely. All right? It's a great question. We'll spend some time on it. All right, good. So this is what we are trying to do. What is super cool here? What is super cool and fundamentally different from other neural network learning techniques is that every node has its own neural network architecture now. right? So the yellow node has the neural network architecture like this. You know, the red one up there has a different one. The green node has a very kind of high fan-out architecture. The blue node D has a very thin architecture, things like that, right? So every node has a different neural network because the neural network structure captures the local neighborhood, captures the structure of the network around this node. And the green node has a lot of neighbors, so its network is very wide. The blue node has very few neighbors, so this network is very narrow, right? But every node has a different network. So the way we will think of this now, how do we initialize these neural networks and how do we compute over them, is that basically at the bottom, the feature vectors we will use as inputs, right? Every node has a feature vector, so x sub a is a feature vector of node A. So this goes at the input, and then this box will take these two feature vectors and aggregate them and pass it on. And then here, this aggregated feature vector from the two neighbors will be combined with B's own feature vector and again passed on. And again here, these representations will be aggregated and then passed on, right? So we will basically think of this as a fixed depth neural network where at the bottom, at layer 0, features of the nodes get input, and then through these nonlinear transformations, some kind of embedding feature representation of a node will come out, right? Notice, what is important to notice here is that, for example, the input at node C are the features of node C. But the representation of node C at this level will be some hidden, some kind of latent representation of the node. And this will be another latent representation of the node. So the input are raw node features, and then everything from here on is happening in the embedding space. Okay? What is also to notice is that if this is 2 layers deep, this means that here in the network we go 2 hops away, right? And if node E would have another neighbor here, this neighbor wouldn't be part of our neural network because we go 1 step, 2 steps, we wouldn't go 3 steps, right? So the deeper we go in the network, right? And that's the argument why we don't want to go 20 steps deep, because essentially then we would just aggregate over the entire network. Okay? So now what is the key distinction between different architectures is how are these boxes, these neural networks in here defined? These aggregation steps that take information from the neighbors, somehow summarize it, aggregate it, and pass it on. So this is where these different architectures will differ. So the question is, what is in this box? What are in these boxes? What kind of operators do we need? Right? And the basic approach, what people tend to do, is to use the average as the aggregator, right? Where you simply average the feature vectors coming from the neighbors. Or here, you average the representations coming from the children. Average is, the reason why people do average is because it nicely keeps things kind of at the same order of magnitude. It turns out that theoretically, most powerful is actually doing a sum. So doing a summation is the best thing you can do. And if there is time, I can give a lecture on these theoretical reasons why. But this is essentially the idea here. And again, notice that summation, maximum, and average are permutation invariant. You can take a summation in whatever order you want, you will always get the same number. And this is important because we don't want this result here to depend in what order we process these nodes, because the order is arbitrary anyway. What is important is that node C has these 4 neighbors, and in what order we enumerate them, we don't care. There's nothing magical about the order, so we want order invariant, right? So the point is that these boxes here will average, in the simplest way, will average the messages coming from the neighbors. And then once we have averaged the messages, we will then apply the neural network, so some kind of nonlinearity. So here is now the description of how this will work, right? So let's think of the following. For every node, I will have a representation, and the superscript tells me at what level of the network am I operating at. right? So at the level 0 of the network, a representation of node V is simply its feature vector, right? Yeah. Then this will be now at the inner layers of the network. I will have a representation for every layer, for a given node at every layer of the network. And then the representation at the final layer of the network is my embedding of the node. Okay? Happy? Yeah? Now I explain what's there. But the point is, this is the 0th layer representation, which is basically equals to the features of the node. This is the last layer representation of the node, the kth layer, and this is the embedding after k layers of the neural network. Now we need to explain what is happening here. Sigma is a nonlinearity, usually a rectified linear unit. That's the thing that people like to use the most. Now, what is happening in here? The way to think of this is the following. What are we doing here is to say, to compute the representation for node V, let's go over the neighbors U of node V, and then let's take the representation of that neighbor from the previous level. Let's average those together, right? We divide by 1 over n. And this is the aggregation, right? So essentially what I'm saying here, I'm node V, I check who are my neighbors. If I'm right now at level k, let me look at who are my neighbors at level k minus 1. Let me take their messages and average them together. Let me transform them a bit. So this will be a parameter matrix. And then I say, oh, and let's add this. Let's combine these messages from the neighbors with the message from myself from the previous level, right? This is node V. This is a node V, okay? So this is what's happening here, right? This is now the representation of node V from the previous layer, right? And this is what is essentially happening. So to understand, we have two transformation matrices. We have some nonlinearity, so that this is now a neural network. We aggregate information from our neighbors. We combine it with our own information and pass it on, right? So if this is at level k, all this is happening at level k minus 1, right? And at level 0, it is just a feature vector, and at the final level, that's my final embedding. So if anyone has a question, now is like a perfect time to ask me something as this sinks in. Sounds funny up here. Any question? Yes, go ahead.
Do you have some approach to make it deeper in some way, like deeper ResNet, like residual connections, to make it more powerful because deeper network is more powerful?
Yes, you are asking whether deeper networks are more powerful. What I'm trying to say is, if you make this deeper, yes, it will be more powerful, but you can only make it so deep because you can go so deep in the graph. So this notion of depth here is different than what you are doing in computer vision, where you are just adding these hidden layers. Here you are capturing much more information because you go farther out in the network, because you are aggregating from neighbors, neighbors of neighbors, neighbors of neighbors of neighbors, and so on. So here you are aggregating more information as you go further out, right? So you are not transforming that information more, but you are aggregating more information. So this is very different because you are learning from your neighbors. You are not learning from one data point anymore. You are also learning from the representations of your neighbors. So you're learning how to aggregate information from your neighbors, right? So now, yes?
Is it possible, for example, the embedding is not computed at the previous layer?
You are, of course, the way I compute this is that for every node I would compute the embeddings at all layers, so that this is always computed, right? So what this, if you unroll this, this is essentially, if I go back to here, this is essentially this type of tree, right? These are H0s, this will be H1s, this will be H2. And for every node, I will have something like this. So the same H1 here is in here in some other neural network, right? If I go back here, right? Like, so this is A1, right? But then this is also A1. So this message and this message will be the same, right? These parts are actually the same in both cases, right? So there is some redundancy, right? And then, you know, this is now HA2, right? And so on, right? So I need to compute embeddings for all the nodes at all levels. Okay, good. Anything else?
If we cannot increase the depth, can we stack them together? Another network which uses ZV as the input instead of XV.
Yes, you can stack them, but it will work the same way as I explained. It will just be deeper, right? So that's possible. So now the question is, how do we train this, right? Like, how do I get this final embedding, and how would I train this? And this was the question you were asking before, right? We need to now define the loss on how to train these embeddings. And what I want to be able to say, what are we trying to learn? We are really trying to learn these two parameter matrices W and V, right? W and B. And these parameter matrices are here to do the transformation. And what the trade-off between these two parameter matrices will be, if, for example, W is all zeros, then I'm not learning from my neighbors. I'm only taking my own features and transforming them. Right, so this would be now just like a multi-layer transformation of my own features. It's just a deep model on my own features. If I make this thing very, very high value, then what this is now saying, it says, kind of ignore your own features, just borrow the data from your neighbors. Right? So this will allow kind of to learn what is the optimal way to enrich the information the node knows about itself. How much nonlinear transformation you want to do over the node's its own feature vector versus nonlinear transformations from the neighbor's feature vectors. And this will become very important in many applications where you can say, I want to predict something about node A, but if I know who its neighbors are and if I know its features, then I can borrow that information to be more accurate about predicting that for node A. You can think about predicting someone's property in the social network. If I know who their friends are and I know the properties of those friends, those properties come here. I can learn how to combine friends' properties with the person's own properties to make the prediction about the person. Right? So I'm learning how to share or aggregate information in the network. Yes?
Instead of having two separate parameters to decide how much information you want from your neighbors versus yourself, why not have one parameter and then basically just, for example, like take for example, if you have like one parameter, you just do 1 minus that parameter and you take yourself's information.
Good point. There are two things happening here. One is that we are kind of trading off between W and B, but both of these are transformations and they are different. So you want to be able to learn that, for example, certain components of features from the neighbors are important and certain components of the features or certain subsets of the features from yourself are important. And the approach you suggested would not allow to do that. So yes, you could try, it would be simpler, but it wouldn't have enough expressive power, right? So this is the idea. So now, right, like I can feed these embeddings into any loss function, right, anything here, and run stochastic gradient to train these weight parameters. Notice that I have one weight parameter per layer of the network. So if I have a 3-layer network, I will have three W matrices and 3 B matrices. So in total, I have 6 matrices to train. Of course, I can train this in a supervised or I can train in an unsupervised way. So I could train this in the same unsupervised way as we did it last week on Tuesday when we talked about, I can use random walks or I can use any other type of similarity metric in the, between the nodes. And now I can say, how do I best set these parameter matrices such that these particular similarities are obeyed. So this would be basically saying, let's try to train things in an unsupervised way. What we can also do is we can try to train things in a task-specific supervised way, right? Like trying to predict type or color of the node, where I can say, if I want to make a prediction about node A, I will now, based on this embedding, make a prediction, and then I can do back propagation into this network to learn the parameters W and B. What I can also do, if I want to do, for example, link prediction, then I would take pairs of nodes, and I would have pairs of neural networks here that are then connected to the final output node. So I can play with these architectures in many different ways, right? So for example, if I would have a drug interaction network, then here the label could be, is a drug safe or toxic, right? So I'm trying to make a prediction about whether this drug is safe or toxic, right? So the way this would look like, let's say in this node classification way, I'm trying now to write out the entire loss function that we try to optimize, right? And basically what do we say? We say, let's go over all the nodes of the network, and then this is called the cross entropy loss. It's just a classification loss, where basically what I'm saying is, this is my embedding for the node V of interest. This is some parameter classification weights. Think of this simply as some vector, and I'm doing the dot product between the embedding and that vector. I'm sending that through nonlinearity, so this is simply a logistic regression. So this is now the probability that V belongs to the positive class, and 1 minus that is the probability that my thing belongs to the negative class. I'm taking the logarithm, so this is now log probability, and then I multiply that with the ground truth label. If I'm doing binary classification, I can think of y to either take value of 0 and 1. And what is then interesting, if y equals 1, then this term survives and this term gets cancelled out because this will be 0, and the other way around, if y is of type 0, then this will be 0 and this term will survive. So essentially, what this will try to do is it will try to maximize the probability of predicting the correct class. It's the same type of loss that we were using when we were talking about likelihood of a given graph, right? We said that for the positive nodes, I want this to be big, and for negative nodes, I want this to be big, okay? And this is now our loss function, where we can take the derivative of this both with respect to these parameters as well as the parameters of this neural network, and then try to estimate W and B, right? So let me now kind of give an overview, right? So given a graph, we want to define the embedding of a given node A. So what do? We first create a computation graph for that given node based on the network neighborhood structure of our given node. And then given that, we now need to define a loss function on the embeddings, right? Some objective function over these embeddings, so that we can then optimize the parameters, try to minimize that loss function, right? And what is interesting is that we can train our model on a subset of graphs, and we can apply this model to graphs that we haven't yet seen. What do I mean by this is that, for example, we take 3 nodes. For the 3 nodes, we create the computation graph, and this could be our training set, so that maybe later on, some new nodes arrive. Maybe these are the nodes D, E, and F. We can still learn the model on these subgraphs and then apply them to those subgraphs. And the reason why we will be able to do this is because we are assuming we will be doing parameter sharing. What do I mean by that is we are assuming that these processing boxes are the same everywhere, right? That W and B are shared across all these different architectures. So when a new architecture comes, I can borrow W and B from these graphs, transfer it here, do the forward pass, and I have a prediction done, right? So the idea is that we can apply our model even to graphs or parts of the graph that we have never trained on or we have never seen before, right? The way why can we do this is because we assume if we have different computation graphs that the parameters governing these aggregations and transformations, these W and B parameters, are shared across different architectures, right? And this is why we are doing it this way. So this means the same aggregation parameters are shared across the nodes. This is cool because the total number of parameters is independent of the network size, meaning the size of this graph, it's constant. And what is also cool is that now we can generalize to unseen nodes or to the unseen parts of the network, right? So because what we talked about on Tuesday was node to vec and deep walk. Those methods cannot generalize to new nodes. Those methods cannot generalize across graphs. Our methods can do that, right? We can train our B and W on some training graph so that when the new graph arrives, we can apply that method to those model parameters to the new graph, which is super useful when you are working, let's say, with molecules or things like that. Or, for example, in social networks, you could imagine you are given some snapshot of the training graph, then some new node arrives, you've never seen it before, but to create an embedding for the node, all you have to do is create the computation graph, and you can make the prediction. So you can transfer the parameters to unseen parts of the graph. Another reason why this is useful is because you can have a super huge graph that's too big for you to train on. So you can only train on subparts of it, but then you can apply the model to all other parts of the graph as well. And that works really well, right? So these are some important benefits of graph neural networks as we define them so far. So to recap, what did we learn? We talked about how to generate node embeddings by aggregating neighborhood information from the network. We just saw the basic idea, the basic variant of this method where we are simply just averaging the messages coming from the neighbors. And the key distinction between different methods is how these different approaches will aggregate information across the layers. And so far, the aggregation was a simple average and then a simple weighted combination of my own feature information plus the average feature information coming from the neighbors. That's the basic. And now I'm going to kind of explain the next iteration of this idea that is called GraphSage. Before I do that, I'd like to see if there are any questions. Yes, go ahead.
Can you elaborate a little bit more on when you mentioned it could generalize to new graphs, like the shared parameters? In what cases is that okay? Because, for example, it doesn't quite make sense to me that you could generalize to like a graph that's like a snapshot from a few years earlier, just because the structural properties would be different. So what cases is that okay and what cases is it not?
Great. So the question is, I made this claim here that you can generalize to new graphs. Of course, you can generalize in a sense that if your if the statistical properties of the data, or if your the nodes are sampled from the same distribution, then you can generalize across that distribution. Of course, if the data generation process has shifted dramatically, then that generalization ability won't be there, right? So I'm not saying that you can train your model on a social network and then apply it to predict whether a drug is toxic or not. That kind of won't work, right? But if you think about saying, I build a recommender system on Facebook today, and then tomorrow a new user joins, you can still apply your model to this new user, right? Because, again, the Facebook did not change too much from one day to another day, right? So the idea is more that the even is not so much about the claim. The claim is not so much about generalization. The claim is even that you can apply it, right? The methods we talked about on Tuesday you would not be able to apply, right? A new node would arrive to Facebook network. You would have to recompute the entire embedding of the Facebook graph. Here, you don't need to recompute anything. You just create a computation graph, and here is your embedding of that new node that you have never seen before. And that's what is elegant here. Yes?
So the maximum depth of your network is 5 layers, because you only explore up to five steps, right?
Correct.
So can you go beyond like 5 layers? So essentially like the number of, let's say the number of nonlinearities is essentially predetermined by how many layers you explore.
You can make, so good question. How deep, like, again, the question is, what do we mean by depth, right? I'm kind of, in some sense, the more decadently nonlinear you want your model to be, you can make it as deep as you like. But I think what we have here is 2 notions of depth. One notion of depth is how much nonlinear transformations, let's see if I go back, right? You can ask, how deep in the network do I go? How much information do I need to aggregate? And that's a different notion of depth than to say how deep is this neural network. And if you think about traditional neural networks, they are one layer deep, right? Because it's one input and then a lot of magic happens and it's one output. Here, if you think about it, you are also increasing the number of inputs you get. So this type of depth is very different than a ResNet depth or a VGG depth or whatever is your favorite model, right? Those types of depth, you can add those decadents here as much as you like, right? But here the fundamental difference is that you are kind of increasing the amount of knowledge you bring into the model, right? So you could make here this part more complex, more nonlinear, several layers deep, if you like. But the depth we are talking about here is different. The depth says how far in the social network do I want to go, and how much information do I want to borrow from neighbors or neighbors of neighbors, right? And if you think about social networks, making a prediction about myself, you don't need to aggregate data from somebody in Africa to make a prediction about myself. You probably need to aggregate data from everyone here, maybe your friends as well, but somebody, I don't know, 7 hops away in an Amazonian forest, it's not clear how much their properties will be predictive of my properties, right? While your properties here might be very predictive of, I don't know, something about myself, right? So you don't need to go too far here. Of course, you can make these parts more expressive, deeper, as you call them. But these are two notions of depth. Okay? Yes?
Can you go to the next one? Yeah. So you talk about that the graph neural nets don't need to recompute every time, like you do that. But this example, you only have like a new node add to the current neural net. If we have lots of new nodes coming, do you need to refresh all the parameters in previous
You don't, if you have many new nodes coming, you don't need to refresh the parameters. Again, I think what we are now saying are two different things. One thing is that essentially you can imagine that every node defines a computation graph. So if I pick a random subsets of the nodes and train on them, I'm able to generalize to this set of nodes that I haven't picked. Now, if you think about the network evolving, these guys that come later, might be kind of fundamentally different than the guys you trained on. Then, of course, you will have trouble generalizing to that. But if you are assuming that the network, let's say, is a static object, but you only train on the random subsets of the nodes, then you'll be able to generalize to whatever else you did not train on. And this is useful because you can have a graph on bazillion nodes, and you can train on a subset of it and then apply your model to the rest of the network. That becomes very important. All right, good. Let me now move on and talk about graph convolutional neural networks, and in particular, GraphSage. Okay? So this is what we talked about so far. We said for a node, let's create the neural network structure around it. And then we will have these little neural networks in here that will aggregate and transform information. So far, we did something very simple where we said, what does the node do? The node takes the average message from its neighbors and adds it to its own message and passes it on. That's what we said. Now let's try to generalize this and make it more general. So the way we will do this now is this aggregation function will look the following. We will say, let's take our own message from the previous level and use this matrix B to transform it. Then we will say, let's take the messages from our neighbors. Here are the neighbors. From the previous level, and let's use some general aggregation function to aggregate this. And then what we are doing is to say, let's now also transform this aggregated message. Let's concatenate these two messages and send them both through the nonlinearity. So what we are doing here is we generalize this by using a general aggregation function. I'll give you examples of that. And what we also changed is, rather than having a plus here and kind of confusing or kind of mixing together information from the neighbors and our own information, now we keep it separate before we push it through a non-linearity. Okay? That's the difference. So to show you again, before this was the type of aggregation we were using. Now our aggregation is different. We have that B, it is down here, so that part is the same, but there is no plus here, there is a comma. So we will kind of concatenate this part with the aggregation part. So this aggregation part is generalization of this summation here. We have the matrix W, and then we have the nonlinearity. So again, two big differences. Rather than summing two things together and kind of losing track of them, we keep them separate by concatenating them. And rather than summing them, we use this general aggregation function. What is interesting actually is that you can theoretically analyze what are properties of different aggregation functions and what kind of functions you should use for different cases. The point is that what we did before, we were simply using the mean aggregation function. We simply took the messages from the neighbors and added them up and then normalized that by the number of neighbors. We can also do a pooling type approach. For example, we could do element-wise mean or max pooling. So this would be another option where here we are again taking messages from our neighbors, transforming them, and then we are applying some kind of pooling strategy where basically we would do the maximum across the coordinate, or we would take the mean across the coordinate. And this is different than what we have up there. And then if you like, you could even use a neural network like an LSTM to be able to learn how to aggregate the neighbors. And of course, LSTM, for those who know, is not order invariant. So when you train, you could try to do this over several random orderings. So to make sure that this thing won't try to be, or that this thing will learn that the order is not important, right? But now we made our model much deeper, as you guys were asking before, because now at the aggregation step, I actually have a proper neural network that aggregates. And in some sense, the depth of this network, if you unroll it, is equal to the number of nodes in the number of neighbors. And here, pi means some random permutation of those neighbors of a given node, right? So this is how we now have generalized this. To make it more complex, we are able to use different types of pooling strategies, and this pooling strategy can even be a learned pooling strategy. Yes?
Is, since usually you want to apply an LSTM when there's some sort of temporal information you want to learn. But it seems like in every other aggregation strategy, we don't really care about the order of the neighbors at all.
Exactly. We don't want it to learn the order. But there is a very nice work that shows that you can make LSTM be order invariant if you if you teach it over random permutations or random orderings.
But then what is the point of using LSTM versus like some other order invariant network?
What's the point? The point is that there is parameterization, there are parameters in here that are still useful to learn, right? So of course you can come up and suggest your own aggregator. That's completely great and awesome. What people have done in the past, they have tried this, they have tried that. If you think you have a better idea for an aggregator, that's an awesome project. There is a deadline. Actually, I forgot. Sorry. I forgot. There is a deadline midnight tonight. So keep it coming. These are great project ideas. And feel free to steal them from each other if you like. That's fine. Yes?
So if you're using an LSTM or any kind of neural network as your aggregator, is it the same LSTM or the same aggregator for all of the nodes?
It is the same aggregator for all the nodes at the same level. Right? We use you could even combine different aggregators at different levels. That's interesting. I don't know if people have tried that. But generally, you would use the same aggregators, the same parameters, whatever B and W, for the same layer. You would allow them to be different across layers, but generally you would share this across all the layers. What you could also do that, for example, nobody has tried is you don't need to share the parameters across all the nodes. You could somehow say, oh, for these nodes I will have one set of parameters, and for this other set of nodes I'll have other set of parameters. If you could somehow decide that ahead of time. I don't think anyone has tried this. So this is all brand new. So the first paper on this was published like 2 years ago, 2017. Right? So the GCN was 2017. This GraphSage was 2018. So this is like brand new, hot off the press, right? So this is not. There's a lot that is unexplored here, and there is a lot that is unanswered here. But this is kind of one of the hottest areas of machine learning right now. If you look at the keyword distribution at the latest ICLR, these types of things were as big as entire NLP. Right? So the graph neural network keyword was as big as NLP keyword at ICLR. Deadline was, I think, a few weeks ago. Right? So these things are very hot because they allow us to model structure in the data in very unique ways. And there is a lot of questions that are unanswered. So I'm really kind of showing you the earliest works in this area. And there is tremendous kind of progress being made from week to week. Okay, so let me conclude. So what did I talk about? I talked about this notion of graph convolutional neural networks, where the basic variant simply averages the information from the neighbors and then adds it with its own information, and we kind of stack these neural networks on top of each other. And then we talked about GraphSage, that what it does, it allows us to basically generalize this notion of aggregation with different aggregation functions and with these types of concatenation, which keeps the information from the node itself separate from the information coming from the neighbors. The way you would efficiently implement these methods is to realize that you can kind of write this very nicely as sparse matrix multiplications, right? So everything that I've written in this way, how you are aggregating from the neighbors, you can kind of write out as a matrix multiplication, where A is the adjacency matrix, D is a degree matrix, same as in spectral clustering, and these are the message matrix from the previous layer. So essentially all you have to implement is this type of iteration, right? So this is extremely cheap. It's just a product of two matrices, and you get the embeddings of all the nodes, right? This is a diagonal matrix, right? So this can be made very easy to implement and very easy to scale up, right? And as I said, this is now 2 years old, right? So the GCN paper. Great. And as I said, there is a lot of follow-up work, and this is all from last year and this year. But essentially, there are nice tutorials and overviews. We will talk in the last 15-20 minutes about attention-based methods. That's kind of the last thing I want to cover. There is also nice work about embedding entire graphs, more interesting work about embedding nodes, methods about that are different from this local network expansion, because these types of graph neural network approaches, even if you make them infinitely deep, won't be able to capture the structure of certain graphs that are kind of have interesting symmetries. So this is super cool. There is very nice connections with spectral clustering. So they're kind of spectral approaches to graph neural networks. There is extensions to this that don't embed into the Euclidean space, but embed in hyperbolic space to allow you to model hierarchies. That is super cool. There is interesting work on pre-training, explanations for these models, and more and more and more. So there is really a lot more I did not talk. Are there any questions? Yes?
How do you incorporate the weights of the edges?
How do you incorporate the weights of the edges? The way you can incorporate the weights of the edges is two ways. One way you could is if you have any weight on the edge, you could, in your aggregation function, you could use that information, right? So the most trivial way to do this would be to do a weighted average rather than just take the average. Another way how you can incorporate weights of the edges is to come up with this notion of attention. Okay, great. So let me tell you about attention. Great question. Thank you for asking it. Good. So let's recap, right? So for graph convolutional neural networks for GCN, this was the formula we talked about, right? You just take the average of the messages from your neighbors and transform it, and then you combine it with your own message transformed as well. So now the question is, how would you learn that certain nodes may give you more information than certain other nodes, right? Maybe strongest friends reveal more information about yourself than some weak friends or some acquaintances. So the idea will be that I don't want to just aggregate information across all the neighbors, but I want to have some weight, let's call it alpha, that will tell me how important is a given edge, right? So for example, right now we just said all the edges are of equal importance, if you think from the average point of view. And what we want to do is we want to explicitly define this edge weight based on the structure properties of the graph, right? So that right now all the neighbors of the given node V are equally important, but we don't want all the neighbors to be equally important. So the question is, can we do better than this assigning equal importance to every neighbor and aggregating? Can we let the weighting factor, this weight, alpha, to be somehow implicitly defined, or can we learn it, right? So the goal will be to set in principle arbitrarily importances to different neighbors of each node in the graph, right? And how are we going to do this? Is that we will compute the embedding of a given node at a given layer, and then we will apply the following, what is called attention strategy, right? Where we will attend to different nodes, or we will pay more attention to different nodes in the network, where nodes attend over their neighborhood's message and implicitly specifying different weights to different nodes in the neighborhood. So we need to figure out how are we going to define this weight, okay? So let's do it the following, right? Let alpha UV be computed as a byproduct of the attention mechanism A, right? And we'll say that let A compute attention coefficients EUV across pairs of nodes based on their messages, right? So the idea is that the edge weight of EUV, so of an edge UV, will simply be some combination of the message, the content of the message at node U and content of the message at node V. And we'll have some transformation matrix and some function A that will combine these two together, right? And the idea is that this EUV will indicate the importance of node U's message to node V, right? And then what we will do is to set the edge weights, we will normalize the coefficients using softmax function in order to be kind of comparable across neighborhoods of different sizes, right? So the edge weight will now be the exponent of the weight computed by this attention mechanism and then normalized. And as I explained last time, if you take an exponent of something and normalize it by the sum of the exponentiated values, then essentially the value that will take the highest weight is the one that has the maximum here. It will basically take all the weight and the rest will be very close to zero. So that's kind of the intuition. This is why this is called the softmax, right? But now I have a weight. So now in my aggregation, what is different is, again, I'm aggregating over the neighbors, but now I'm also having the weight here. This alpha UV that comes from here, where EUV comes from there. Okay? And now the question that we need to decide next is, what is the form of this attention mechanism? How would we go and learn it? So here is the idea for the attention mechanism. There can be kind of the approach to choosing this attention mechanism function A. So this function up here, it's kind of, we are agnostic about it, right? So in some sense, you could use a simple single layer neural network. This function A can have parameters which we would need to estimate. And the point is that these parameters of A are trained jointly with the neural network, the aggregation neural network itself, right? So we learn the parameters of this attention mechanism A together with the weight matrices W and B that we talked about in an end-to-end fashion. And for example, the paper from iClear last year by Velichkovic, he showed that you can actually even do like a multi-attention or a multi-head attention, where the idea is that for every edge, you will learn R different weights and then attend over all these R weights at the same time. So essentially what this means is that to stabilize the learning process of the attention mechanism, attention operations in a given layer are independently replicated R times. So in some sense, we are learning capital R different attention weights for each edge, and then the outputs are aggregated or concatenated across these R different functions. So what are some key benefits of this, and why would you want to use these kind of weights on the edges and learn them? So this allows us to basically in learning or specifying different importance values of different neighbors. And these importance values can be learned based on the feature representations or the messages that these neighbors are sending to you. This is computationally efficient because this computation of this attention mechanism can be parallelized, and aggregation may also be parallelized across all the nodes of the graph. It is also storage efficient because all we need to store is the information about the nodes plus the information about the edges. So this is still linear in the size of the graph, and it has a fixed number of parameters regardless of the graph size, because that attention mechanism is just a function that we are applying across all of the graph. And again, it's trivially localized in a sense that it attends only over the local graph neighborhoods. And it's still inductive, meaning we can still apply it to nodes we have never seen. We can apply it to the graphs we have never seen. So to give you an example, here is a graph of a citation network where every node is a paper, edges are paper citing each other, different papers belong to different subject areas, different areas of science, and the goal is to predict what is the subject area of a given paper, here indicated by color. For example, the way this works, if you only use the text of the paper, your accuracy would be 55%, right? So if I just say, I take the text of the paper and I try to predict the discipline of the paper, I would do 55. If I, for example, would use the methods that are graph-based, like we talked about deep walk in the last lecture, deep walks get 67. So far better than 55, right? But if you, for example, look at the graph convolutional neural networks, what we talked about today here, that raises the performance to 81%, right? So we went from 55 to 67 to 81. And now if we add this graph attention mechanism that I talked about, that further increases here for 2% to 83, right? So you see how being able to combine the textual information, so the way to think of this, right? So this is the text information at 55. Deep walk only looks at the graph information, 67. If you combine both of them together using the graph neural network, you get 81. If you add the attention, it further improves the performance, right? So this is one example of how learning attention can really help. Are there any questions? Yes?
For attention, is there a reason why they stopped at just converting to a scalar multiple instead of learning the whole map from the node and its neighbor to some vector representing the neighbors? So they map the node and its neighbor to a scalar multiple.
Yeah.
That scalar times
the message.
Yeah. And it just have a linear map that converts vector to vector. So in theory there would be more power to that. Right?
So let me understand. So what you are saying is rather than have attention per edge, you are now learning an attention per edge, coordinate. Right? So that's what I guess your vector thing would do. You would say for every part of the message, I learn a separate attention weight, right? Because you would do this kind of vector, not a dot product by product by coordinate, right? So you'd be scaling each dimension of the message independently. That's what you would be doing.
Yeah,
And right now we are scaling all the components of the message equally.
Yeah, I guess like the point is like this current thing is just like the nonlinearity attention part is only captured in like
one scalar rather than the entire way. That's an interesting thought. The question becomes how unstable the learning process is and whether you could make the learning process be stable. But you are right that your idea would be strictly more powerful. All right. Anything else? Yes, go ahead.
For weighted networks, would you encode somehow like the weights of edges into this attention and the convolutional network?
Good question. So if you would somehow have a weighted network, then I think what I would do is I would use one option would be to simply say, I'll take the weighted average. So you use the weight as your attention. That's the simplest, clearest, the first thing you would try. The second thing you could try is to extend your attention mechanism A to be dependent both of them on the messages as well as the weight of the edge. That would be another option. And this means that you'd be able to learn kind of to trade off between the content of the message and the weight of the edge. That's also, I think, a good idea. So these are kind of two ideas that come to mind right now. All right, good. Let's see, what do I have? In the last 5 minutes, I can show you an interesting industrial level application of this that has had a huge impact. Okay, so this is the application. I like to show this. So this is Pinterest. Pinterest is people take these images and they save them into different types of collections. And the point is that the same image, maybe about some kitchen with a blue fireplace, can get saved into many different collections, right? Maybe some architects creates a collection called blue accents, and they save images that have some blue accent on them, right? Somebody else might be interested in renovating kitchens, so they are saying, okay, here are some kitchen ideas I like. And somebody else is like interested in fireplaces, so they have some fireplaces saved into their collection. And the point is that you now can have a huge graph with the way you can think of this. You have these images and they are saved to collections. And in this graph, this is now a bipartite graph, you have about, let's say, 4 or 5 billion of these images, you have another 4 billion of these connections, and you have about 200 billion edges here, right? Where the same thing can be saved tens of thousands of times into different collections. And what you can do is you can now interpret this as a graph to be able to do better recommendations or understanding of the content in the graph. So the idea will be the following. If you just look at the image of each of these objects, then computer vision will many times make silly mistakes like this, where you are confusing the bed rail and a garden fence. Or for example, you confuse brown rice and soil. Or you confuse the carpet on the floor and this kind of decorative carpets that go on the wall that are more like art, right? So these types of things, computer vision makes a lot of mistakes. So the question is, can you use this bipartite graph to learn how to borrow information from nearby nodes in the graph so that you can really resolve what is similar and what is different, right? Because a bed like this that might confuse you for a garden fence will appear in the graph together with other beds, and you can use the image information from other beds to really say this is a bed. And a garden fence like this one will appear in the graph together with other garden fences that may not look like beds, and you can use that information to learn to distinguish these things together, right? And if you have these types of embeddings of nodes, which are now images, you can then do various kinds of tasks. So let me show you the idea. The idea is that we have this bipartite graph, and we will take, right, where we have images belonging to collections, we will take these images and we will embed them into the embedding space such that the similarity in the embedding space will correspond to some kind of user engagement signal. And of course, the way we will create the neural network is that we will kind of unfold this graph a couple of times, right? So it's clear how this guy will collect the information from here, this thing will collect the information from that pin, and so on and so forth, right? So we will unroll it. And the way we will learn the embedding is to say, we will see what users like to click together. So if a user is looking at a cake, then a user clicks on a related cake. But the user does not click on a very nice comfy sweater, right? And the way we will try to create the objective function is to say that the embedding of the cake 1 and cake 2 should be closer together than the embedding of the cake 1 and the sweater, right? And that is essentially what we will be doing. One thing I did not make super explicit, but I hope everyone sees, is how you can unroll this bipartite graph in several steps to create a neural network, as I was showing you before, right? And essentially what this means is to create the embedding for a given image, you will borrow from other images that are next to it in the graph, right? And you will kind of learn how to best use your own information with the information coming from your neighbors. And if you do this, I'll skip. This is how well this works. For example, if you evaluate, if you just use the visual information, let's say you do 0.23, this is mean reciprocal rank, doesn't matter. If you use text-based only, you do worse than the image, but not too much worse. If you combine the two together, you just concatenate them, you do 0.37. If you use the graph-based method that combines visual and textual data, you get 0.59. That's almost like 50% better than without doing it. And to show you, let me just show you two examples. Here is one example where you can say, if I have this query, what are nearest neighbors in the embedding space? If you do based on visual only, if you do it using this approach. And you can see how this porcelain doll gives you all kinds of porcelain dolls. And here you can see some mistakes that are kind of similar in style, but they're not porcelain dolls. Or I give you another example about cats. If this is your query, notice that it's not clear why these things don't work so well, but notice how here you're getting all kinds of cats. Notice how these things are kind of not necessarily visually similar, but it's all cats with these kind of funny heads. So what did I try to tell you here? The point is that using this graph information, we can learn how to enrich information at a given node using the information coming from the nearby nodes. And this greatly improves the embeddings we can create. So with this, thank you very much. So I'll see you next week when we'll do a hands-on session and teach you how you can code some of these methods. Thanks a lot.